So thank you for your introduction, and I thank Johannes and his colleagues for arranging this wonderful workshop. And it is my great pleasure to visit Darmstadt at the first time. Okay, so the title of my talk is the Tokyo QKD Network for Long-Lived Systems. The contents are as follows. We first discuss requirements for long-lived systems, and then propose our schemes, which is based on secret sharing with quantum key distribution, QKD. We first introduce our field testbed, Tokyo QKD Network, and then present our architecture of a long-lived system. And then we describe our implementations on the testbed and make analysis on it. And I summarize my talk with some future perspectives. And this work was done by many collaborators, and the Tokyo QKD Network is constructed and is operated by NICT, NEC, Toshiba, NTT, Gakushuin University, Hokkaido University, and Mitsubishi Corporation. As for secret sharing, we collaborate with cryptographers at NICT and Tokyo Institute of Technology. And as for long-lived system, we collaborate the colleagues here of TU Darmstadt. Okay, now let me discuss my understanding on the requirements for long-lived system. So we want to make a system which can transmit and store and process the critical data securely for a century scale time span. And I think there are 4 requirements. One is the confidentiality. So the data should be accessible only to authorized parties. So we use information theoretically secure encryption. And the second point is integrity. So data should remain unaltered since stored, and we employ signature and authentication scheme. Third point is availability. The data should not be lost even when a disaster happens, so should be available whenever required. So we usually prepare some redundant data backup and implement fail-safe mechanism. Fourth point is functionality. So data can be processed without encryption. And this is an increasing demand in data centers and cloud services. So we need full homomorphic encryption. So our proposal is actually distributed storage network. So multiple copies of data are created from the original data and stored in the multiple different data servers. And we use secret sharing scheme. And this scheme can ensure confidentiality of storage, availability, and functionality. And we should also employ digital signature and authentication schemes to protect integrity. But it is sufficient to ensure short-term security for certain period until resharing of the data. And we introduce QKD to ensure the confidentiality of data link. So this is the whole picture of our proposal. So let me briefly describe how secret sharing works. So data owner have some secret data S, and then document owner creates a certain polynomial, and then this constant term corresponds to the secret data S, and further generate coordinates, multiple coordinates as shares. Okay, and they are stored in these data servers, which are called shareholders. Okay, shares themselves need not necessarily be encrypted, but just distributed. And the coefficient of these polynomials are deleted covertly. To reconstruct the data, owner collect sum of shares, K of shares, and then try to find the polynomial f of x by interpolation, then this constant term f of 0 corresponds to the secret data S. Here, with shares less than k minus 1, then the original data can never be reconstructed. So this is the Kn threshold scheme. Okay. Actually, with shares less than k minus 1, there remains infinitely many possibilities of polynomial. We cannot specify uniquely with the smaller number of shares. This enables information theoretic confidentiality. Now, with more than k of shares, polynomial can be exactly specified. So sum of shares can be lost. And for example, if n minus k of shares are lost, data can be reconstructed. And this enables availability. And furthermore, shares can be added and multiplied and satisfying the functionality, I mean full homomorphism. Okay, so this is the basic scheme. But this Shamier's secret sharing scheme itself cannot realize integrity. And the security of channels for data transmission is just assumed. So we introduce QKD for confidentiality of data link and also employ digital signature and authentication scheme for long-term integrity. Okay. So now let me briefly mention the QKD. I mean the definition of a QKD link. So QKD link consists of transmitter and receiver and two channels connecting them. One is the quantum channel connecting encoder and decoder for transmitting quantum signals, and the other is a classical channel connecting key distillers. And Eve, who can have unbounded ability, can tap both of the channel, however, cannot access to the internal part of the encoder, decoder, and key distiller. So this is the assumption. And encoder and decoder authenticate with each other, and this classical channel should also be authenticated. And we use Begman-Carter authentication by using part of the key generated by the QKD link. Okay, and we implement a private channel by encrypting the message with the key in one-time part. So we can implement an information theoretically secure private channel. Okay, so this is our basic building block. Now let me briefly mention QKD. QKD just protects the security of data transmission, not storage itself. It works in a point-to-point link, but not in a multi-party link. And the speed and distance of direct link are still limited. Roughly 1 megabits per second at 50 kilometers, or 1 kilobit per second at 100 kilometers. So QKD link itself has the limitations, and actually it is not easy at all to find killer applications of QKD. So it's kind of annoying and makes me stressful sometimes. And I had a nightmare so far sometimes. And one day, Japanese Prime Minister Abe appeared in my dream. And I was in the cabinet office explaining how QKD is important for the government. Then the Prime Minister Abe says that QKD is vulnerable to denial of service attack. Hence, it is not an option of Japanese government. I said, no, we have a rerouting mechanism, but I had no voice. And I just woke up and, oh my God. So anyway, QKD can have a practical meaning in a form of network. So networking is made by introducing the trusted node and by relaying a key via the nodes. Rerouting function is important in practical operation. So we should have an appropriate redundancy, even if such sort of small scale network. Okay, redundancy is important. Okay, trusted node. Trusted node should be protected physically. Eve cannot enter into the trusted node. And we also implement many countermeasures against cybersecurity attack. And keys are relayed by one-time path encapsulation. So let me intuitively show how we can carry out the key relay. So first, each link generates a secure key. And then we perform a one-time path, encryptions and keys are relayed, and then key pairs can be shared between two terminal nodes, even if they are not directly connected by a QKD link. Okay, and we constructed the Tokyo QKD network in 2010 and has been operating this testbed for various purposes. And currently it consists of three kinds of QKD schemes. One is BB84 by NEC and Toshiba, and the other is continuous variable QKD by Gakushuin University and SecureNet, and the other is a differential phase shift keyed QKD by NTT. And recently we have also introduced quantum stream cipher by Tohoku University. And these QKD link constitute a point-to-point QKD link, and each link generates the keys in its own way. And then the keys are pushed up to the key management agent. This is a PC. Key management agent is located at each site, works as a trusted node. And these KMAs are connected by classical authenticated channel and constituting the key management layer. And in this layer, key is relayed. And we also introduce a key management server for centralized management. And this server monitors link information and gathers various information from the key management agent and organizes a routing table and provisions the secure path when some of the links are hacked. And in order to support variety of applications, we also introduce key supply agent KSA, and all the necessary application interfaces are implemented in this key supply agent. And this layer stack constitutes the QKD platform, and secure keys are supplied to the application layer. And the key from the QKD platform can be used in a variety of applications. And we have developed many applications, including a secure smartphone and secure TV conferencing systems and secure drone communication network, medical records system, and secure IP router. And this time, we implement secret sharing scheme in the same application layer. Okay. But before that, let me show one example of our application, which is the QKD enhanced multi-user smartphone network developed by NEC with our collaboration. So keys are generated in the QKD platform and relayed, and then supplied to the application layer. Application layer is a star type network, and a session initiation protocol server, SIP server, is located at the center node and manage the keys. And then this network-centric architecture allows an efficient key management and realizes a key exchange for AES implemented in the smartphone. Okay, now we move on to our architecture of the long-lived system. So the basic framework is depicted in this way. So there are two main systems. One is the distributed storage network based on secret sharing and QKD and protect long-term confidentiality. The other is a system consisting of timestamp service, evidence service, and verifier to provide proof of existence of the document based on commitment and timestamp, and ensure the long-term integrity. And the detail of the architecture will be presented by Dennis just after me. So in my talk, I focus more on this distributed storage network. So this is the actual implementation of our testbed. So in application layer, we implement secret sharing scheme, and there is a document owner and 4 share folders. And they are connected by the black line, which represent private channels. So private channels are encrypted with keys by one-time part supplied by this QKD platform. Okay? And we have to make some assumptions in our system. So trusted node of the QKD platform, this is a kind of a problem. It's not easy to physically realize this trusted node. First, we should put it in a vault. It's a really expensive vault area and need to be protected at the expense of necessary cost. I think this is the most expensive part of the system. However, document owner and share folders are outside of the vault areas. We assume that they are provided by the kind of a storage service vendor, but the QKD platform are supplied to the big carrier companies, for example, and we set the point of interface between these systems, and access rights to the platform and these application layers are completely separated. So this is our current assumption. And we should also realize some secure key transfer from the key management agent to the share folders or document owner. It is not trivial. They are usually connected by a classically protected channel, mostly a tamper-resistant metal cable or short distance. So we use a part of key to authenticate each KMAs and share folders, for example. We also install some one-way firewall on top of the key management agent to prevent Eve from sending a malicious command from the application layer. Okay? So this is the assumption, or we just implement these sort of pieces. So implementation of secret sharing itself is just making a software and deployed in our testbed. Our new contribution may be on integrity protection, and in this conference we'd like to present 2 kinds of implementation. One is a single password secret sharing authentication, also using Wegman-Carter message authentication code, which is published 2 weeks ago in this journal. It took a long time actually since our first submissions, and papers relayed from the journal to journal in a hop-by-hop fashion, and finally arrived at these scientific reports. So this scheme is user-friendly because we use the password. Password is very convenient, but also we can ensure the information theoretic security. So we consume lots of keys. Actually, the key size is 30 times as long as the document size per a store retrieval cycle. So this is one implementation. The other implementation is timestamp chains of unconditionally hiding commitment, which was developed by the collaboration with the TU Darmstadt and NICT. In this scheme, cost for generating and maintaining a proof of existence is independent of the document size. It's really cost effective and will be presented by Dennis later on. So let me explain this first implementation. So we use a 3-3 threshold scheme as a tutorial example. In our real system, we use a 3-4 threshold scheme. But it's really hard to depict in one slide, so I just use a 3-3 threshold scheme. So we have a document and make 3 shares by using the second order polynomial. Okay? And we use a single password. Password has been used in many cases because it's simple and convenient. However, it is not completely secure, usually computational security. So in our scheme, we make shares of password, and distribute the shares in the multiple holders. And then we can appreciate the convenience of password, even ensuring the information theoretic security. So this is a kind of a new element. Okay, so let me explain how it works. It consists of 12 steps. So thank you for your patience in advance. So firstly, owner creates and sends shares of document and password, okay, and using the second order and first order polynomial. So blue boxes are document shares, black boxes are password share. And then each shareholder generates random numbers, okay, Ri, and then makes shares of random numbers by using first order polynomial. So we have totally 9 shares of random number. Okay, this is used for masking the document share later. Furthermore, we generate shares of 0. 0 means the origin of the polynomial by using second order polynomial such that f of 0 is 0. Okay. So the purpose of this process is to mask the document shares in the reconstruction phase. So anyway, we have 9 more shares, green boxes here. Okay. Then shareholders communicate with each other to exchange sum of shares, and these boxes surrounded by blue lines were exchanged. Okay. And sixth, it's a data reconstruction phase. Owner try to remember the password, let's say P prime. Then generates the shares of P prime by using the first order polynomial, and owner sends the password shares to the shareholders. So totally 27 shares are created. It really consumes lots of key. Now, shareholders compute 3 kinds of quantities. One is the sum of shares of random numbers, something like this. And the other is the Z, sum of shares of 0. And using these quantities, holder finally compute this quantity, share F, which is basically document share, but also include difference of password shares masked by these random numbers R and Z. Okay? And then shareholder send these blue boxes, shares F, and then discard the remaining random number shares or shares of 0. So owner have these 3 shares. So owner can reconstruct the polynomial by interpolation, something like this. Now we use the password. If the password is wrong, then this first term remains non-zero, and these 2 terms can mask this document shares, so no information is leaked in the reconstruction phase. Okay? On the other hand, if the password is correct, we can just have a simplified expression for the shares, and note that the property of 0 shares, I mean F0 is 0, then we have these relations, and from this constant term, we can have the original data. So it's congratulations, and this result was press released to the public 2 weeks ago and was very well received. So next time I'd like to have a good dream, and Prime Minister Abe is saying QKD is good, isn't it? Okay, anyway. So I make an analysis of our implementation or more on the future work. So we would like to go beyond the limit of threshold number K. Okay, this is the assumption, but in practical situation, an active attacker may move around the shareholders. Then it is likely that the number of corrupted shareholders must increase as time elapses. So we apply proactive secret sharing in which renewal of shares are carried out at certain interval. Okay, so when certain time interval elapsed, we renew the shares, and each shareholders exchange the shares. So at each time, keys are consumed. So I think one of the bottleneck of the performance is the key rate of QKD. So this is the summary of our Tokyo QKD link, and the slowest link is something like 10 kilobit per second. And to prevent from being bottlenecked by this slowest QKD link, keys are relayed between the key management agent in an appropriate manner. Then the minimum throughput of key supply to the private channel can be raised up to 40 kilobit per second, but no more than that. So this is one of our bottleneck parameters. And I think one important measure for the performance of secret sharing system is the document size we can handle. And this is determined by this quantity. Now T sub s is an interval of the share renewal, and times key rate divided by n times n minus 1. N is the number of shareholders. And let's assume time interval is 10 years, for example, and there are 4 shares. Then using our current key rate, the document size we can handle is just 131 gigabyte. So this is not so big, I think, I'm afraid. And key rate could be 1 megabps at 50 kilometers in a few years by current technology. Then the data size could be as large as 3.3 terabytes, which corresponds to the human genomic data of 4,100 persons. I'm not quite sure this is enough or still really poor size, but anyway, in future, if we want to deal with the petabyte size, we have to increase the QKD key rate up to 1 gigabps, maybe at 50 kilometers. It is a quite challenge, and we may apply dense wavelength division multiplexing, just prepare many QKD transmitters, receivers, including 1,000 channels, and we process whole channel by the really fast key distillation engine or something like that. So having this kind of new application, I really want to increase the QKD key rate at the moment. Okay, so to summarize, we present our principal demonstration of a long-lived system, and confidentiality is realized by the secret sharing with the QKD. QKD protects the private channel. Integrity, we show 2 implementations, and I told mainly on password secret sharing scheme. Another scheme, timestamp chains of unconditionally hiding commitment, will be explained by Dennis after me. Future work is the implementation of proactive secret sharing. Then maybe our testbed can be really practical. And we continue to improve our QKD key rate. And then I hope this sort of direction could be a kind of a killer application of QKD, and I hope some users would be very pleased, including prime ministers or some government peoples as well. So that's all. Thank you very much.